Okay, so we're live on YouTube. Uh, Once again, welcome everyone to the third session of the Summer of ML workshop series. I will start with some brief logistics. So today, firstly for the Q&A, if you're watching on YouTube, please put your any questions that you have in the chat, and we will keep monitoring it and relay it to Ananye. If you're on Teams, then you can just put your message either in the chat or you can raise your hand, and then Ananya can look at your doubt and answer it as and when he feels comfortable. Second, we will have quizzes. We will have a quiz after the session, which we have prepared. So that will be there on Google Forms. And so don't worry about it too much right now. After the session ends, we will give you the link to the Google Form, and then you can use that to give the quiz. Third, since this has been stretched for say like a month-long thing now, and there are there are 4 to 5 workshops which cover a lot of topics, and we want you guys to practice and learn further after the series also. So we have created channels for these workshops, for each of the sessions in these workshops on our Discord server. So if you would like to discuss any of the topics that we will teach you in the workshop series with other people, or if you would like to put your queries or anything that you may come across while practicing and ask them to other people or us, then please join the Discord server and you can interact with other people there. Third, the website for this event, I have put the link again in the message, and you can check it out. In the agenda section, you will find the resources for every session. You will also find, after the session completes, say for the first session, we have uploaded the slides as well as the notes that Pramit wrote on his iPad. So you can check out any resources that you would like to from there. And lastly, like I told you before, the GitHub repo that we have prepared will contain resources for all the sessions, and it also contains our assignment, which we gave out last week. So if you want to get some practice in for the first 2 lectures, you can check it out. It has some pre-written code, and we hope that it will guide you through everything. Okay, so logistics done. I will now introduce Ananya. It is a pleasure to have him here. Ananya is a graduating student in the computer science department. He has been previously an intern at Microsoft Research, and he has also recently published a paper in a top ML conference. So when we talk about seniors who are doing amazing work, Ananya is very, very close to what we mean. And today he will talk about an introduction. He will give an introduction to logistic regression, and he will also introduce deep learning and a little bit of hands-on PyTorch to you guys. So without further ado, I would like to invite Ananya, and thank you for joining us today.
Okay, hi guys. Thanks for the very generous introduction. So I'll start straight away. Maybe you need to give me some permissions because I can't share the screen, and I cannot see the chat either.
Oh, okay. So I added you as a member to the team just before the meeting, but I'll give you the permissions also. Just a minute. I've made you a presenter now.
Maybe I need to rejoin because I can't see it. Give me 1 second.
Sure.
Yeah, is my screen visible?
Yes, it's visible.
Okay. So yeah, so just going over the topics again. Today we're going to cover logistic regression. So logistic regression is one of like another one of classical ML algorithms which you might have covered in previous lectures. So it's closely related to things like linear regression, binary classification, and all of those things. Uh, Heuristic regression will lead us into a gradient descent. A gradient descent is a way of um, optimizing functions. So, given a function you want to find its maximum or its minimum value, then you gradient descent is a general purpose tool for doing that. And gradient descent is pretty much used um, in everywhere in machine learning. So, any type of machine learning algorithm or deep learning algorithm that you study that is optimized using gradient descent. So logistic regression will lead us into like it will motivate the need for gradient descent. Then I'll talk about a perceptron, and a perceptron is a simple. Um, so it's a single neuron. It's a so this, I will explain what a neuron is like through so neurons used in deep learning. So a single neuron is called a perceptron, and I'll explain what that is. And then I'll talk about how combining perceptrons in different ways leads to neural networks. And basically, lots of perceptrons, when you combine them together and train them jointly, that is called a neural network because it's a network of neurons. And that is, and big neural networks, which have lots of layers, are also called deep networks. And this is really what deep learning is. Deep learning is basically um, lots of neurons combined together in interesting ways. And then I'll talk about PyTorch and basics of PyTorch, AutoGrad, and also we'll do a small demo in PyTorch and we'll train a simple neural network. Right.
Ananye, just a minute. Can you put it in landscape mode also?
Okay.
Also, your sound is a little low.
Okay. Is this better?
Yes, it's much better.
Right. So starting with logistic regression. So let's say you have a data set D, which consists of points, right? Consists of points xi, and each point is also labeled with a label yi, and there are n such points. Oh, by the way, if anyone has any questions, because I can't see Teams right now, so maybe someone can relay the questions to me. So that would be great.
Yes, I'll relay the questions.
Yeah. So if you have a data set like this, right, which has n points, and each point is an m-dimensional vector, and each point or each label is either +1 or -1. Let's say you have a data set like this. So a real world example of this data set might be something like, let's say you have the point. So the point is into, like, it's a two-dimensional point. The point is in 2 dimensions, and there are 2 dimensions. So maybe one of the dimensions is temperature and the other dimension is blood pressure. So for a particular person, you can measure a temperature, and like a person can be represented by the temperature and blood pressure. And a person can either be COVID positive or COVID negative. So let's say you have this data set. So you randomly do a random study on a group of people, and some of them turn out to be COVID positive, and other people turn out to be COVID negative. Right. So this is your data set, and the problem you'd like to solve is, given another random person xi, you want to find yi. You want to figure out whether that person is COVID positive or COVID negative, right? So this random person might not necessarily be in the data set. Right? This point might be somewhere here, or this point might be somewhere here, might be somewhere here. So you can imagine that given lots of points in this data set, you can begin to figure out a pattern between the temperature and blood pressure that relates the temperature and blood pressure to the COVID
to whether that person is COVID positive or COVID negative, and you'd really like to learn a function which can tell you what is the likelihood that another random person is COVID positive or COVID negative. So that is what really logistic regression is. Logistic regression is a way of learning such a function. It's one way of learning such a function. So how do you go about doing this? In deep learning, what generally happens is, or sorry, in machine learning, what generally happens is that you try to parameterize. So you want to figure out some function, right? And you write the function that you want to figure out as it takes as input obviously your data point, and it also takes as input a set of parameters theta. So theta is also a vector, and you take both of these as inputs, and you try to predict the probability that a person is, let's say, COVID positive, or you try to predict the probability of a particular COVID test result. And f is a function that you define based on your own knowledge of the domain, right? For example, in this particular scenario, you might think, okay, I can look at the data and I can see that maybe a fairly simple function might like there's a fairly simple decision boundary, or maybe there's a fairly simple boundary that separates these 2 points. So maybe you can have a simple linear boundary that separates these 2 points. So based on this, you can figure out what a function f is. But there's also a set of unknown parameters theta that you figure out through some optimization procedure, and we'll talk about what that optimization procedure is. So essentially, what you need to do is figure out the set of parameters theta that best describes your given data. So one way of doing this is to figure out theta, is to figure out parameters that maximize probability of labels. Right. So what I mean by probability of labels is that given lots of points xi, what parameters theta what is the optimal set of parameters theta that will maximize the probability of all of these labels. So essentially, what is the value of theta that maximizes this? Right. So this gives you a function. Actually, this function will also have yi as an input. So f of x, I'll write it like this. So you can imagine for different labels and different points, you take this product, and what you want to do is find the parameters theta that will maximize this product. So what that set of parameters theta essentially describe is one function f that is going to give you the maximum probability of assigning the labels yi to points xi. And because you know that y, like all of these points in the data set yi are actually the correct labels, so and you're maximizing that probability, so you can expect that on unseen labels as well, these parameters theta will describe well, like will be a good description of how y is related to xi. So that's essentially the idea behind logistic regression. So what is the form of the function f that we choose in logistic regression is this. Right. So this is just the form of the function that we choose, and you can also, this function is called the sigmoid function, and it's also written as sigma. So yi transpose epsilon. Right. So you can imagine that. I mean, this is the reason you choose this function is that this function has the property that it lies between 0 to 1, and it also has the property that f of xi plus 1 theta plus f of xi minus 1 theta is equal to 1. Right? And this is something you would expect from probabilities. That the probability that that the COVID test is positive plus the probability that the COVID test is negative should always be equal to 1. And you can verify this. This is really simple to verify because when it's +1 here, this will be 1 over 1 plus e to the power xi transpose theta. And then when it's -1, it will be 1 plus e to the power minus xi transpose theta. And then when you add them up, it becomes equal to 1. So I hope this notation is clear, right? Theta, like xi transpose theta. So basically here what we are choosing is that theta should be again an m-dimensional vector. That's just, we just choose that theta is an m-dimensional vector, and then theta transpose xi is then or is equal to xi transpose theta. These are just the same thing, and this is just the dot product of xi and theta.
There is a question in the YouTube chat.
Yeah.
So it says, how did the maximization go to the multiplication of probabilities? Could you explain that?
Because this is a intersection of events, right? So the event is that so let's say you have lots of points. You have x1, xn. So the probability that, so what you really want to find is the probability that you assign all the correct labels. So the probability is that, so the way you would say it is that x1 has label y1 and x2 has label y2, right? And x3 has label y3 and so on. So whenever you have and all of these events are independent, then you take the product. Essentially that's how it works. Because, so I mean, another example might be that let's say you're throwing let's say you're rolling dice, right? So so if you're rolling a die, when someone asks you what's the probability that you get 1 on the first roll and 2 on the second roll, then you'll multiply the two probabilities together. Probability of 1 on the first roll is 1 by 6, and probability of 2 on the second roll is 1 by 6. So the probability of the compound event is 1 by 36. So it's essentially the same idea. That's why you take the product. Okay. Right. So once you have this function, you know everything, right? So essentially, the optimization problem that you want to solve is you want to find theta, the best theta. Let's call that theta star, which maximize this product. So you can also write this, similar like this, right? 𝐷𝐼𝐴𝐴𝐴. Just take the log of this, because maximizing this is the same as maximizing the log of this. So this will become I've just changed xi transpose theta to theta transpose xi, because this is like the way we usually write theta transpose xi, but they're the same thing. Right. So you want to maximize this quantity, and let's call this quantity j of theta, or the error function. So j of theta is called the error function. So this is what you want to compute. Now, the standard way of computing like the minima or maxima or any function is to compute the gradient and set it equal to 0. So the gradient of this function is, like, you can figure this out using chain rule. So because it's the log, this goes in the denominator, and the derivative, like the gradient of this is just yi xi, and basically what you want to solve is this equal to 0. Now it turns out that you cannot solve this equation in a closed form. So there is no closed form solution. No closed form solution for this. And the reason is that, I mean, this is a very weird sort of equation. You have, because you have exponentials, and then exponentials are multiplied by these by these xi quantities and yi quantities. So you can't really solve this equation to get a theta. So you have to figure out some other procedure of solving this equation, and that procedure is called gradient descent. So the idea is very simple. I can motivate this idea. So let's say you have a function, right? This is your function, and you are at this point. So let's say your parameters, you start somewhere here. Let's say you choose randomly some set of parameters, and so this is j of theta and this is theta. So I'm just taking a special case where theta is one dimensional, which is different from this case. But yeah, just to motivate. So let's say you choose some random theta and that falls there, and you want to minimize j of theta. So one simple thing you can do is to take the gradient at this point, right? So you take the gradient at this point, and what the gradient really gives you at this point is what is the direction in which you should move, where the function decreases the fastest. Right? So the gradient is negative, which means that if you move in the negative direction, then the gradient is the function is going to decrease the most. So you can take, so once you've got the gradient and you know the direction, you move a bit in that direction. You take a small step in that direction, and you come to this point. And then you can do the same thing. You can take a small step. You can compute the gradient here, and then take a small step in that direction. And then that gets you to this point. And then you keep doing this until you arrive at, let's say, at this point. And at this point you find that like the gradient becomes very small, right? So what you essentially do is when you move in a particular direction, you weigh the size of your step by the value of the gradient. So as you get closer and closer to this minimum, your step size becomes smaller and smaller until you arrive very close to this optimal point. And at that point, basically your theta starts changing very little, or your theta starts oscillating, and then you can say, look, your algorithm has converged, and you are very close to the optimum. Even in multiple dimensions, this works. So let's say you have a two-dimensional parameter space. So your parameter theta, so this is theta 1 and this is theta 2, and theta is theta 1, theta 2, right? And j of theta, so I can draw some contours for j of theta. Right? So I hope you know what a contour is. So a contour is basically a curve on which a function has a constant value. So j of theta has a constant value on this ellipse, and j of theta also has some other different constant value on this outer ellipse, this one, and then it has some other different constant value on this outer ellipse. So this is essentially how this is just a representation of j of theta. So you can imagine that maybe this is j of theta. If you represent it in 3 dimensions, it's a hill, and this is near the bottom, or it's a valley, and this is near the bottom of the valley, and this goes to the, like it's basically like a canyon, something like this. And this is the bottommost contour, and this is like a contour at the near the top, and so on. So again, let's say you start from this point, and we know that the gradient is the direction of the steepest descent. So which will obviously be perpendicular to the contour. So this will be your direction, and then you take a step in this direction. And again, once you come to this point, you get a new gradient, and then you take a step in that direction, right? And then you can see that eventually, once you keep following the gradient, you will converge to the minimum, which might be somewhere near the center of this center here. So in general, we can write gradient descent for any function j as follows. Right. So compute. So start with random parameters theta I, theta 0, right? And then you do compute for I until convergence. You start with I equal to 0, and until convergence, you run the following procedure. You do theta I plus 1 is theta I minus alpha times the gradient with respect to theta, of j of theta evaluated at theta I, and yeah, and then you iterate, like you bump, like increase I by 1. So this is simple algorithm. Basically, you compute the gradient at each theta I, then you subtract the, like you move in the opposite direction of the gradient, because the gradient is the direction of the the steepest increase. So you move in the opposite direction, and then you keep doing that until you converge. And convergence criterion, typically there can be lots of convergence criteria. So one convergence criteria can be that theta changes very little. Another convergence criteria can simply be that you run for fixed number of iterations. And yeah, so and another convergence criteria you can basically see is that let's say so that's really in the context of deep learning, but essentially what happens is when you're optimizing some function, you can compute I'll just leave that. Maybe I'll talk about it later when I'm doing the PyTorch demo. But essentially this is the main idea. Now coming to alpha, what is alpha? So alpha is some parameter that you have to choose based on your own knowledge, right? So typically alpha is very small. So alpha, you might choose alpha equal to 0.01 or 0.001 and something. So alpha is typically depends on how complicated your function is. So if j has a lot of curvature and j is a very complicated function, then you'll choose very small alpha. Because if your alpha is large, what might happen is that you take a step that is too large and you overshoot your local minimum. So you keep oscillating over the local minimum and don't never really get very close to it. But if alpha is too small, then what might happen is that you take very small steps, and then it takes a lot of iterations to actually converge. Okay. Now this is gradient descent, and you notice that j of theta is like, if you look at the gradient for j of theta, you can see that you're taking, like you're doing the iteration over all points, right? You're doing the iteration over n points. So in general, this takes time proportional to n. Right? So the time is proportional to n, and typically in deep learning or in machine learning, n is very large. So you might have n in the tens of thousands, and when n is in the tens of thousands, computing each of these gradients becomes very expensive, and therefore each step becomes very expensive, and therefore you might not be able to take a lot of steps. So what happens in practice is that you take, essentially you subsample some points. So essentially don't take the gradient over n points, you take the gradient over some subset of these points selected randomly, and that variant is called stochastic gradient descent. It's also called SGD, and this is essentially what you use in practice. So it's very similar. Like the only difference is that this gradient is not computed over all points. It's just computed over some random subset of points. So you choose random subset of points. So let's say you choose random subset of n prime points, and then you define random subset S of points. So then you define j of theta is summation I equal to 1. Sorry, I in S f of xi yi. Right. So when you do this computation, essentially what you're doing is you're approximating the gradient, right? Because you can imagine if n is very large, let's say n is 50,000, then you're taking lots of points and summing a gradient together. But if you just subsample 5, let's say you just take 50 points, you can imagine that it gives you a reasonable sort of approximation of the gradient. And when you do in fact, you can show that in expectation, stochastic gradient descent converges to gradient descent. So it's the same as gradient descent in expectation. If you do lots of stochastic gradient descent steps, then it's the same as doing gradient descent on that function. And if I were to show stochastic gradient descent on this point, on this function, so you might imagine that the gradients calculated using stochastic gradient descent are not exactly the gradients of the, they're not always accurate. There are some small errors in the gradient. So instead of going in this direction, this might go in this direction. Right? But the errors are random. So sometimes the errors you make are random, so they tend to cancel out over time. So you might go in this direction, and then you might go in that direction, and then you go in this direction, right? And then you go in that direction, and so there's some randomness associated with how you move in the parameter space. But in expectation, you tend, like over a long period of time, you tend to generally move in the right direction. And so this is a very useful trick, because now you don't have to run over, like you don't have to run over a very large data set. Even if your data set is very large, you can choose S to be very small. And usually, like, batch sizes are very small, right? The size of the subset S is called the batch size, and the batch sizes are usually very small. They can be as small as 50 or even 25. Right. So the idea now is that we can optimize this objective using gradient descent to get a set of optimal parameters theta. So once you have the set of optimal parameters theta, how do you figure out what is the label for a new unseen point xi? So what you can do is you can pass it into your function, right? F of xi. So we can find the probability of, let's say, you find the probability of COVID test being COVID positive. Right? So if this probability is greater than half, so you can have some threshold, right? Let's say your threshold, very natural threshold to choose is half. Right? So let's say your probability is greater than half, then you can declare that we are COVID positive. So if the probability is greater than half, then you declare you're COVID positive. If it's less than half, then you declare that you're COVID negative. And this essentially gives you a way of finding, like, predicting test positivity on unseen data. Another interesting thing, so if you notice that I drew a straight line here. So why is this line straight? So this is called the decision boundary, and the decision boundary is basically separates points which your model will predict are positive and negative, right? So all points to the left on this side of the line, your model will say that they're COVID negative. All points on this side of the line, your model will say that they're COVID positive. How can we derive like the equation of this line? So if you notice, your threshold is half, right? So the one way to derive the equation of this line is to find all points for which this probability is equal to half. So this is equal to 1 over 1 plus e to the power theta transpose xi. And if you solve this, you can see that this implies theta transpose xi yi should equal, actually y is plus 1, so I don't need to write that, is equal to 1, which implies that theta transpose xi is equal to 0. And if you think about it, this is just the equation of a straight line. So in general, logistic regression will give you all decision boundaries that are a straight line. Now, obviously, like if someone asks you, if you wanted to develop your own method, right, you can generalize this. So maybe your data is very complicated and a straight line really can't fit it. Maybe you want something like a quadratic function. So instead of logistic regression, where you put theta transpose xi here, maybe you can think of putting some kind of quadratic function here. So maybe you can think of putting some quadratic function like x transpose theta x plus theta prime transpose x plus c, or something like that. So really, logistic regression is just one example of how you can solve this problem. But you can just develop your, like, there can be infinite number of ways in which you can solve this problem, and it all depends on your own insight into how this data, like what kind of model would work best, and what kind of decision boundary might exist, and how much data you have, and all of those things. So a lot of machine learning is essentially figuring out which kind of model is best to choose. But logistic regression is the most widely used in such situations, and I mean, you'll find this in, like, this is a very standard function. So if you are using something like a Python package, logistic regression will always be present there, and you can just call a function to do logistic regression for you, and it often works very well in practice. And so that is why logistic regression is really popular. So any questions on this?
There was just one question about why the threshold was half.
Yeah, that's a good question. I mean, it's not necessary that the threshold should be half. But I guess in the absence of any other information, right? Because the way you're modeling it is so basically the function f, right? The function f is going to give you the probability that someone is COVID positive. Right? So in the absence of any other information, if the probability for something is more than half, then you're going to, if you're asked to make a prediction, right? If you absolutely have to choose one or the other, then you will, like, it's rational to say that someone is COVID positive. Right? So basically, if someone tells you that, look, I made a model and the probability that a person is COVID positive is 70%, and then they put a gun to your head and say, what is, you have to choose one or the other. What is the prediction you're making? Then the answer, you will, like, the rational answer to give is that the person is COVID positive. But you're right that it's a very important, like, it's a limitation, right? That you always don't want to, like, if you're only 70% certain, if you're saying that someone is COVID positive with 70% probability, then it probably is not a good idea to categorically assume that the person is COVID positive. And again, that's a limitation of I guess logistic regression, and it's more generally, like, it's a limitation of this procedure, right? What you're essentially doing is you're trying to maximize the likelihood of the labels, but you don't really care about so it might be that in your example it's very harmful. Let's say false positives are really harmful, right? If you wrongfully declare someone to be COVID positive and they're really COVID negative, then it's very harmful for you. Maybe you have to incur a high cost. So in that scenario, what you really want to do is you want to change your objective function. So you might want to add a term here which penalizes wrong prediction, like it penalizes false positives more. So all of these are, like, again, more advanced techniques, and you can read about them. But if you have something if you want to do a very simple sort of machine learning, if you want to fit a very simple sort of machine learning model, then you will do logistic regression. Another thing you can do here is, because your model is giving you confidence predictions, right? Your model is explicitly saying that 70% with 70% probability, I predict that someone is COVID positive. Then you can take a decision based on the confidence prediction. So if your model is 70% confident, then maybe you don't trust your prediction as much. But if your model is 99% confident, then you say you trust the model prediction. You say, look, this person is probably COVID positive. So yeah, I guess that's one thing you can do. And in general, machine learning models, I mean, this is a big problem in machine learning, that your models can never be 100% correct, and there's always someone, you will never get 100% accuracy. You'll probably get 70% accuracy, 95% accuracy, and sometimes it's not even possible to predict whether a particular prediction is correct or not. So at least in logistic regression, you are getting some sort of confidence that your model is outputting.
There is another question about what was the time complexity of gradient descent?
Okay, so I mean, you want the full time complexity, or is the question about why this is order n?
I guess Kanishk, you can unmute and ask your question.
Sir, I thought, sir, am I audible?
Yeah.
So I thought you mentioned that the complexity of gradient descent depends upon the number of sample cases.
Yes.
So does it not depend upon the number of parameters?
It does, obviously. So I said it's proportional to n, but it's also the proportionality. I said this time complexity is proportional to the number of samples, but it's also proportional to the number of parameters and other things.
Okay, right. So sorry, so I got it.
Okay. So after logistic regression and gradient descent, I think we can move to talking about another kind of model. So just like logistic regression solved the binary classification problem, you have another type of model that can solve this problem. It's called the perceptron, right? And the perceptron is, so basically it arose out of, so lots of people were studying neurons in the brain, and then they thought of maybe having this sort of stylized representation of a neuron in the head, right? So the way a neuron works in the human brain is that basically you have you have this you have this neuron which has all of these which has some inputs coming into it from other neurons, and it also has outputs going to different places, right? So what happens is that one end of the neuron is stimulated with by different other signals from other neurons, right? So lots of signals come in, and then when these signals cross a certain threshold, the neuron gets activated and it sends signals out to other neurons. So they thought maybe let's try to have like a mathematical object that models this neuron, and let's see what we can do with this. So very simple sort of representation. So you have a neuron which has lots of inputs. Let's say x1 through xn, and okay, maybe I should call this x1 through xn, and this is parameterized by some vector theta, and it gives some output z. So z is equal to some function f of theta transpose x, where theta is again this vector theta1 theta n, and x is equal to x1 xn, and f is called the activation function. So it controls how theta transpose x. So maybe if theta transpose x is very large, then you output a certain kind of value. There are lots of activation functions that you can use. So one activation function you might use is let's say something like the step function. So or maybe something like the step function. So step function looks like this, right? I'm not sorry. I'm not. It's not called a step function. It's called something else. I'm forgetting the exact name. But that function is basically that f of x is equal to 1 if x is greater than or equal to 0 and 0 other points. So this is one activation function you can use. So basically this neuron will only activate if x is greater than 0. Otherwise it will stay 0. Another function that you can use is called the ReLU function. So ReLU looks like this, right? F of x called the ReLU. It's short for rectified linear unit. So f of x is equal to x is greater than 0 and 0 otherwise. Another function that we saw previously is the sigmoid function, right? We saw this in logistic regression as well, and the sigmoid function looks like this. So when x tends to infinity, you go near, like you go to 1, and if x tends to minus infinity, then you go to 0. And if you look carefully, you can see that the sigmoid is really sort of a differentiable version of this. So maybe a differentiable or soft version of this. Because if you want to use gradient descent, then you need to have differentiable functions. So sometimes when you want behavior that's similar to a step function, you tend to use a sigmoid activation. So these are some kinds of activation functions that you can use. But what is a perceptron good for? Well, you can use a perceptron for classification, binary classification problems, right? So similar to I mean, if for example, if your activation function is this, right? If your activation function is this, then you can fit a perceptron to do binary classification. So let's just take an example. So let's say you want to fit a perceptron to the AND function. And the perceptron has two inputs, x1 and x2. So you have 0, you have 1, and 0, 1. So if you want to mark this, so this thing is going to be, right? So your output is, I'm going to mark 0 outputs by red. So when x1 or x2 is 0, then you're going to have a 0 output, right? Because anything ANDed with 0 is 0. And when you have a positive, both of them are 1, you get a 1 output. So let's say your activation function is again the step function, or no, not the step function. I'm not sure. If someone knows what this function is called, maybe you can tell me. But I forget what the name is.
ℓ𝐻𝐵.
Yeah, ℓ𝐻𝐵. Yeah, ℓ𝐻𝐵 function. So let's say your function f is ℓ𝐻𝐵, the ℓ𝐻𝐵 activation function. So what you really want is to find theta such that theta transpose or theta1 x1 plus theta2 x2 is greater than 0 only when x1 comma x2 are both greater than 0. So actually I missed one thing here, and that is that in general you can also have this plus b term where b is also a parameter. So I mean, technically you can think of this as just having an additional input. So you have x1 through xn, which just comes from the data, and you also add one here, and that gives you an additional input. And when you take the dot product, you get this constant term here from the parameters. So essentially, what this problem now becomes is theta1 x1 plus theta2 x2 plus theta3 is greater than 0 only when x1 and x2 both are greater than 0. So one way of solving this problem might be to, so you can't use gradient descent here, but you can do just hit and trial and figure out what set of parameters satisfies this equation. So one set of parameters that I can see satisfying this equation is theta1 is equal to 1, theta2 is equal to 1, and theta3 is equal to minus 1. So you can see that for these choice of parameters, the function becomes x1 plus x2 minus 1. This is only positive when both x1 and x2 are positive. So basically, such a perceptron will now represent the AND function. And in general, you can see that because like for any sort of activation function that you use, f of theta transpose x, because of this, because it's a linear function, like a linear function here, you're only going to be able to represent linear decision boundaries. So your decision boundary will always be linear, right? Because this is a linear function, right? In general, like f of theta transpose x, let's say your decision boundary is f of theta transpose x is equal to some constant c. Then you solve it. You are always going to get theta transpose x is equal to some other constant f inverse of c, and therefore your decision boundary is always a straight line. So you might think that, look, this is and you'll be correct. And the idea is that perceptron is fairly limited in terms of what kinds of functions it can represent. So it can only represent functions that are linearly separable. So a single perceptron is fairly limited in its representational power. So for example, your perceptron will never be able to represent the 𝐸 function. The 𝐸 function looks like this, right? This will be 0. Sorry, this will be 0. This will be 0, and this will be 1. And you can see that this function is not linearly separable. You cannot draw a straight line that separates the negatives from the positives. So you cannot represent this using. This is not representable using a perceptron. But so how do you solve this problem? Well, this problem is solved by essentially having a stacking perceptrons. Right. So one way you can implement the 𝐸 function is by having perceptrons that can implement. Let's say you have one perceptron that can implement the 𝐸 function, and then you pass that into another perceptron that can implement the NOT function. Sorry, what I'm saying. That's NOR. So 𝐸 is basically not A and B, or A and not B. Right. So because each of these is linearly separable, and is a linearly separable function, and all is a linearly separable function, then you can have perceptrons that implement the and not function, and function, and OR function, and then you can chain them together to get. So basically, how you chain logic gates, and then you can get a 𝐸 function. So that's the idea, right? When you stack perceptrons, you can get many kinds of different kinds of functions. And in fact, in general, you can stack perceptrons like this, right? So you can stack perceptrons in layers. So let's say you have one layer which takes inputs, right? And then the outputs of these perceptrons are then passed to another layer. So basically, this output goes to all of these perceptrons, and this output goes to all of these perceptrons. This output goes to all of these perceptrons. So basically, the output of each perceptron in this layer is connected to the input of each perceptron in the subsequent layer. So in this way, you get a large sort of network of perceptrons, and this is called a neural network. I mean, this is one type of neural network. It's called a fully connected neural network, because each perceptron in one layer is connected to every perceptron in the second layer or the subsequent layer. So it's called a fully connected neural network. And the idea is that when you stack perceptrons like this, the representational power of these perceptrons increases. And in general, there's a theorem, right? There's a theorem that if you have enough layers and if you have enough perceptrons, then you can basically represent any function. You take any function, given enough perceptrons and given enough layers, you can represent that function exactly. So that basically shows the representational capabilities or representational power of these perceptrons. So is there any questions on this? And then I'll go into detail on how these neural networks work. No questions?
There was one. Yeah, Anirudh.
Yeah, I have a question. So regarding the ReLU function, because it's unbounded, and if you have a multi-layer network, won't the perceptrons deeper in the network end up taking very large values?
I mean, they theoretically can, but in practice, I mean, that doesn't happen, right? So for example, let's say your activation function is just identity, right? Let's say your activation function is not ReLU, it's identity. So f of x is equal to x. So you can actually see that you will see that your multi-layer perceptron is essentially just matrix multiplication. So I'll just start by describing some mathematics of this. So let's say you have this is one layer, right? This is the ith layer. And the ith layer, let's say, has Ni perceptrons. And each perceptron gets so there are Ni minus 1 inputs. Ni minus 1 inputs from the previous layer. Let's say the parameters of this perceptron for the first perceptron, the parameters of this perceptron are theta I1. Parameters of this perceptron are theta I2, and so on. Right? So we can arrange this into a matrix. Theta I is equal to theta I1, theta I n. So this matrix describes the parameters of all perceptrons in the ith layer. The output of this perceptron is Zi1, Zi2, and so on. Right. So you have n outputs, and this is a vector. So you know that, like, just based on what we start, like what perceptron is, you have Zij is equal to theta ij transpose and the outputs from the previous layer. Right? So Zi minus 1. I hope this equation is clear. So if any questions on this equation, then like now is the time to ask. Okay, so you can write this in matrix form. Zj, so not Zj, Zi, which is now a vector, is equal to theta Zi minus 1. Theta I Zi minus 1. Theta is a matrix, right? So notice that here I've omitted the activation function. So in general, this will be Zi is equal to theta I f of theta I Zi minus 1. But right now, let's assume that there is no activation function. So what will happen? What is the output of the nth? What is the output of the last layer? Zn is equal to theta n Zi minus 1 Zn minus 1 dot dot dot, right? So this will be equal to theta n minus 1 theta 1 and z0. Z0 is just the inputs. So theta n minus 1 z x 1 x, right? X. So you can see that this is just a matrix, right? So this is going to be some matrix m times x. So without activation functions, even stacks of perceptrons are not much better than just like simple matrix multiplication. So they're not very powerful. But notice that without activation functions, if your activation function is identity, right? Identity looks like this, and this is unbounded. So even if this is unbounded, you can see that if your parameters are bounded, like your parameters are small numbers, then mx need not be unbounded. So essentially, I mean, your output might blow up, even if like our output might blow up if your parameters are large numbers. So if let's say your parameters, all of them are around 2, right? And then when you multiply a lot of them together, your output might become very large. But in practice, what you choose is parameters initialized like from some normal distribution. Let's say you choose parameters initialized from some normal distribution centered around 0 and with, let's say, variance 1. So this is typically like how you initialize your layers. And when you do sub initialization like this, the parameters tend to be very small. They tend to be smaller than 1, and therefore like your outputs don't explode. So I hope that's clear. I mean, in general, there are some problems where you get exploding inputs or exploding outputs. So you might get exploding outputs, and you also have this problem called of exploding gradients. And I'll explain what I mean. I won't go into much detail about this, but I'll briefly explain what the problem of exploding gradients is. So you can also have this problem of exploding gradients, and that happens when your parameters or your gradients grow very large, and when you keep multiplying them together, they can become very big. So there are techniques to prevent such problems, and one of the techniques is to initialize parameters suitably so that these things don't explode. So I hope that answers your question. I mean, I'm not going into much detail here, but because there's not much time. But maybe you can read about it. So there are different kinds of initialization techniques like HE initialization, Xavier initialization. So all of these kinds of initializations, which are there to prevent exactly this sort of problem. So again, this problem can also occur with sigmoid activation, right, which is bounded. So it's not really a problem of the activation function, but it's it's just a problem of how neural networks are structured, because the inputs are feeding into the next layer and so on and so forth. So what can happen is that your outputs explode. Or your output can also grow very small, in which case it's called vanishing outputs or vanishing gradients. So this is a problem that you have to deal with, and there are various ways to solve that problem. Okay. So I actually wanted to derive backpropagation rules, but I'm not sure if there will be enough time for that. But I'll describe like what this is essentially. Right. So in general, what your equation for the outputs is Zi is equal to theta I Zi minus 1 plus Bi and some function, activation function f. And this activation function can actually also be layer dependent, so it can also be fi. And Bi is again just a bias, just a constant term that you want to, that is dependent. Like this is a vector, and for each so here you can add a Bij. So again, this is just a constant term that I talked about above. Just you add a constant term, so that even when your outputs are 0, you still get some constant value. You still have some value that you can learn. So this is basically the equation, right? So at the outputs, so once you get the output, right, your output will be Zn, and then you will have some predicted output which is Y, and this will be passed to some error function J. So some error function will get Zn and Y as input, and then what you will do is you will try to minimize the error function using gradient descent. So basically what you want is this gradient with respect to parameters theta. So basically what you want is the following sets of gradients. So you want gradients with respect to each theta ij, and also gradients with respect to each bi. So this is essentially what you want to compute, and you can actually do this using like vector calculus. It's not that complicated. So maybe I'll just describe briefly how this can be done. So so let's say you want to compute this theta ij with respect to this. So if you look at this diagram, each of these theta ij's is actually influencing this output zij. So you can actually use the chain rule, right? So what you can do is you can take the derivative of j with respect to zi g, and then take the gradient of theta ij with respect to zi. And this gradient is easy to figure out because Zij is equal to f of 𝜃𝐼𝐽 transpose ZI minus 1 plus BI. Right. So this, you know, this is this in terms of 𝜃𝐼𝐽. So you can find the gradient easily and plug this in here. So if you know this quantity, then you can figure out this quantity. Similarly, gradient of BIJ, or this is not a gradient anymore, derivative of J with respect to Bij is equal to derivative of J times right. So again, you know this exactly, like the Zij is a function of Bij, so you can easily figure out the derivative from here and plug that in here. So really all that's left is to figure out this. So in order to figure this out, you can use induction. So you can you know that right. So you know that Zij, so in this particular, yeah, so in this particular diagram you can see that each Zij feeds into each of these feeds into each of the next perceptrons in the next layer, right? So essentially Zij influences each of the subsequent outputs. So Zi plus 1 through Zi plus 1 Ni plus 1. So each of these outputs is influenced by Zij. So you can use this rule from multivariable calculus. So basically for each variable that you influence, you need to take the you need to use the chain rule and sum up all of the terms. So from k equal to 1 to Ni plus 1, you go divided by Zi plus 1 k. Right. Okay. So again, this term is something you know by induction, right? Because what you're doing is you're calculating the derivative for n first, and then n minus 1, and then n minus 2. So when you're calculating the derivative for I, you already know this derivative just by induction. And to figure out this derivative, again, you can use the equation, right? Zi plus 1 k is equal to f of 𝜃𝐼𝐽 transpose Zi plus Bj. Actually, yeah. So once you know this, you can take the derivative Zi plus 1 k with respect to f prime of this quantity times 𝜃𝐼𝐽k. So basically now you have all of the terms that you need, and then you can use all of these terms to figure out the derivative with respect to each parameter. So if you look at these equations very carefully, what's happening is that these gradients are flowing backwards. So you compute the gradient at the output first, and then those gradients are used to compute the gradients with respect to parameters in the penultimate layer, and then in the layer before that, and so on. So essentially inputs, when you push the inputs from the left side, and those inputs go to the right side to compute the outputs, but the gradients flow from the right to the left. So the gradients will go from, you compute the gradient at the output first, and then you propagate the gradients backward. And this process is called backpropagation. This process is essentially called backpropagation. And this is essentially how you train neural networks. So any questions on this? I know I went through this a little fast, but hopefully the main idea is clear. Essentially, you have the neural network itself is a huge function with parameters theta I, and then you're differentiating that function with respect to each of the parameters. That's all this is. It's not. It looks very fancy, but it's very simple actually. You can even derive this on your own after the lecture. Any questions? No questions? Okay. I guess we can then start with the PyTorch tutorial or introduction. Give me 1 second. Yeah, by the way, if anyone has any questions or you can feel free to ask.
I had a small doubt in the equation for zi plus 1k.
Yeah.
Shouldn't it be theta I plus 1k instead of j there?
Yeah, you're right. It should be theta I plus 1k. Sorry. I think I stopped sharing my screen, but the equation will then be zi plus 1k is equal to f of theta I plus 1k transpose zi plus bi plus. Yeah, you're right. Thanks for pointing that out.
We can see the terminal.
Yeah. I'm going to show PyTorch on the screen.
Okay.
Right. So PyTorch is essentially this library that allows you to do deep learning and basically takes away a lot of the does a lot of the heavy lifting for you. So just a show of hands, how many of you have used NumPy before? One person. Okay. 8 people. Cool. So a lot of PyTorch is very similar to NumPy, but because a lot of you haven't used it, I'll just go from the beginning. So import torch is basically the standard way of importing the PyTorch module, and torch has these objects called tensors, and tensors are essentially multi-dimensional arrays. So, for example, you can have if you declare torch tensors like this, like you say torch tensor, and then you pass in your array. So I can pass a 2D list. So when I pass a so when I pass in a 2D list, I get x, which is a tensor, and that gives you a tensor. So all of these tensors have you basically have all of these standard operations defined on them. So let's say I declare some other random tensor. So you can do lots of things. So x is this, y is this. So you can multiply two tensors together. So when you do x times y, you basically get pointwise multiplication. So 1 times 0.5, 0 times so 1 times 0.5, 0 times 0.1, 0 times 0.1, and 1 times 0.6. That's pointwise multiplication. You can add two tensors together. It's just again pointwise addition. You can subtract. You can do matrix multiplication. So at does matrix multiplication. So x at y is matrix multiplication, and this multiplies two tensors together. You can sum tensor entries together. So let's say I do torch dot sum. That will sum all of the entries. I can sum along a dimension. So if I do dimension is equal to 1, it will sum along the row dimension. So 1 plus 0 is 1, 0 plus 1 is 1, and that gives you this tensor. So I mean, there's a huge list of operations. I cannot go through them all in one lecture. And basically the way to learn these is to just keep practicing. And when you keep practicing, when let's say you want to do some particular operation, right? Let's say you figure out, okay, how do I take the sigmoid of some tensor? Then you Google it. You'll see. Okay, torch sigmoid function. Right? Let's say Google this, and then you pretty much you'll get your first result in the PyTorch docs. Will tell you how to do that particular operation, and there will be examples. So you read all of these examples, and over time you start to figure out how you can do all of these operations. But the basic idea is that you have these objects called tensors, and you can do operations on them in this manner. So you can, if you add, so you don't have to individually add all of these entries together, but you can do the operations in this batched manner where all of these entries are processed together. Another so this is just NumPy stuff, right? Now, NumPy is also another library that does all of this stuff. So what's the difference between PyTorch and NumPy? The difference is that PyTorch has automatic differentiation. So if you do some operations, PyTorch will automatically track what operations you are doing, and then it will be able to back propagate through them automatically. So let's take an example, right? So let's say I have x1 is one tensor. So I'll just take a random tensor. So torch.random basically gives you a random tensor of a given shape. So when I say 3, 3, it will give you a 3 cross 3 random tensor. So I get two tensors, x1 and x2. Okay, I'll take this. X1 is also, let's say these are random tensors. Let's say I want to have tensors where I track the gradients. I track what gradients are being backpropagated. So I pass this argument requires grad is equal to true. Requires give me 1 second. Right. So here's another tensor. X1 dot requires grad. So you can set these requires grad attributes, and that once you do that, then PyTorch will start tracking gradients with respect to these two tensors. So let's say you have you compute some output, right? X1 dot transpose, X1 transpose at X2. Once you do that, you will get this tensor, and you can see that there is a grad function associated with it. It's called dot backward. So essentially, what's happening is that it's tracking your gradients. So in order to, let's say you want to compute gradients, right? So what you do is z dot backward. So what PyTorch just did when I do z dot backward is it's computing gradients with respect to z of x1 and x2. So it's computing gradient of x1 like gradient of z with respect to x1 and then storing those, and then computing gradients of z with respect to x2 and storing those. So if I do x1 dot grad, I should get those gradients, right? x1 dot grad, and when I do x2 dot grad, I get the stored gradients. Now if you look at, like, you can just compute the gradients manually, right? Is x1 transpose x2, so the gradient of z with respect to x1 is x2, and the gradient of z with respect to x2 is x1. So if you look at x1 dot grad is exactly equal to x2, and x2 dot grad is exactly equal to x1. So this automatic differentiation, this PyTorch does at the backend, and this is implemented for all functions. Like any function that PyTorch has. So for example, the sum function, the sigmoid function, ReLU, everything. There is a, like, it can backpropagate gradients. So essentially, what this means is that you can write neural network. You just have to write the forward pass, how the inputs are transformed to the outputs, and then you don't have to do backpropagation. You don't have to write functions for backpropagation. All of that is done in the backend. You just have to call z dot backward, and this is the, like, a big benefit with PyTorch. Any questions here? I mean, any questions with the automatic differentiation? I mean, that's I think the biggest differentiating factor in PyTorch. Other things are just, I mean, sort of library functions and all of this. Okay, no questions. So one thing I can do is, like, maybe we can do a simple, maybe we can do this simple sort of demonstration in PyTorch. I mean, there will be a lot of unfamiliar things here which you might not have seen before. In the sense that, I mean, I gave you a very brief introduction of PyTorch, and so I'll use a lot of functions which you might not be familiar with. But I guess the main idea should be clear to you. So let's do MNIST classification. Right? MNIST classification is again, you can do this on this is Colab, right? Google Colab. Google Colab is this online environment where you get free GPUs, and you can basically do experiments on Colab if you don't have a GPU at home, and you can learn to implement different models. And I think this is the best way to actually learn machine learning, is to try to implement different things on your own and to try to code as much as possible. And that's how you learn PyTorch. Nobody can teach you PyTorch in a single tutorial, or you will never be able to learn all of the functions in a single tutorial. It's just through practice and through all of these tutorials, through writing a lot of code, that you'll get to learn PyTorch. So yeah, we don't have a lot of time. How long can we stretch this, Ramneet? I mean, is it okay if I go 10 minutes over?
Yeah, I don't think it should be an issue.
Right. So we'll implement a simple neural network to do MNIST classification. So I'll start with importing Torch and importing Torch Vision. So Torch Vision is just a library that's used to do computer vision. It's also like released by, it's also in the, like, the Facebook has made Torch Vision, Facebook has made Torch, but it contains a different set of functions for computer vision. Right. And I'll also import matplotlib. Now we can, one thing we can do is to get the training data set, and PyTorch again has the training data set. There's a very convenient way to download the data set. So torchvision.datasets.mnist. So I'm not sure if you guys know what MNIST is, but MNIST is basically this very famous data set of handwritten digits, and it's used as almost like a hello world for machine learning, and you can always, like, download this very simply. So I'm just writing code to download this data set. Right? So basically what I did is I specify the root. So root is basically which directory this data set will be stored in, and dot means they store it in the current directory. Train is equal to true means I want to download the train split. So train data set means that all of the data that is given to you for learning. That's the trained data set. And then I download is equal to true means just you're allowed to download, and transform basically means that so the images in this data set are in a different format. So this converts it to PyTorch tensors. The images are converted into PyTorch tensor. And similarly, I can just get the test data set. So this will take too long to download. I actually downloaded it here in a different order. Maybe I can show. Correct. Yeah, so I can show this here. Right. So the data sets can be indexed like an array, right? So you have a data set and you can figure out the length of the data set, which will give you the number of training points in the data set. You can, let's say you want to find the 10th point in the data set. So you can do 10. That gives you the 10th point. And this point, so the point has two values. It's a tensor and a label. So if I do 0, that gives you the tensor, and I can actually print the tensor. I can show you what the tensor looks like. Right, so this is a 3, and you can also see what the label is. The label is 3. This is what the data set looks like. Then I can define these helper functions called data loaders. Right. So basically, what the data loaders do is they take the data set as input, and then they'll give you random batches from the data set. So they will let's say I specify batch size. My batch size is equal to 50. So what they will do is they will pick the first 50 images, then they'll pick the second 50, then they'll pick the third 50, and so on. So basically, it's a convenient way to get batches from the data set. And I can also do shuffle is equal to true. So this will randomly shuffle the data set beforehand and then give you 50 images and labels at a time. So this is a convenient way to do stochastic gradient descent. You don't have to write a function to generate random batches. It just does it for you.
Ananye, can you zoom in if possible?
Oh. Is this better?
Yes, much better. Thank you.
Okay. Right. Next, what we want to do is we want to define the network. So to define a network, we have to declare a class. And this class, so I hope you know what like classes. I mean, classes are basically objects which are a collection of like different functions and different variables. So it's just a compact way of representing different functions and so on. And in PyTorch, any neural network that you want to declare, it has to be a class, and this class has to inherit from. So it always has to be a child of the torch.nn.module class, and basically torch.nn.module has some useful functions, and all of those functions you don't have to write yourself; they automatically become a part of your class. It's just a convenient way of again writing a function. So you write the initialization method. So again, this is just a standard way to initialize a class that is a child of another class. Now we can write fully connected layers. So again, if you want to implement fully connected layers, PyTorch again gives you simple primitives to implement these layers. You don't have to write matrix multiplication and all of those things by yourself. It's automatically done for you. So I mean, you can look at, I think if you want to learn PyTorch in general, it's always a good idea to look at docs. So you should get into the habit of reading docs. So if you search for the docs for, let's say, PyTorch, you want to implement a fully connected layer, so you do PyTorch fully connected layer, and then you get this. Sorry, this is Google. I mean, if you go to ignore this. PyTorch and then linear. So you get this documentation, and that gives you everything about this layer. So it tells you that it applies a linear transformation y is equal to xa transpose plus b, where a is parameters. So this is exactly what you need, right? And then it gives you the input. It says that the input is of this form, and then the output is of this form, and so and basically how it also gives you examples. This is how you can declare a layer, and then this is how you pass input to the layer, and this is how you get the output. So all of these things are just defined in the docs for you. So in general, whenever you want to define something, it's a good idea to Google and see if it's already defined for you in the docs. So let's say you want to define a neural network where the first layer has 100 units and the second layer has 10 units, because you want, like, there are 10 digits, possible digits, so you define 10 units in the output. So 28 squared, because this image has dimension 28 plus 28. So the input, so when you squeeze the input into a vector, it will be 28 squared, and then the output is 100. Self-fully connected layer 2 is 100 and 10, because the output is 10. And then you want to define your activation function. This is the softmax activation. The softmax activation is related to sigmoid. You can think of it as being related to sigmoid, but when your output is multi-dimensional, or if you want to output, like, say, one class out of 10 different classes, because like a given digit can either be a 1, either be a 2, 3, 4. So when you want to output a probability distribution over different classes where only one of them is correct, then you use the softmax distribution. So basically you can think of this as taking in a random, like, some vector as input and then transforming it into a probability distribution. So nn dot softmax and then torch dot nn. Sorry. And then you can define a forward function. So the forward function takes input x, and then it gives you the outputs. Self. Actually, you don't need this, right? Let's omit this. So I'll tell you why I omitted it later, but let's assume that you just have two fully connected layers now. So x is equal to self.fc1 of x is equal to self.fc2 of x, and return x. So basically now you pass both of these, like the input, through both fully connected layers and return it. So that's just it's very simple MNIST network. Now you can define, like, you can instantiate this. You can find an optimizer, or rather, let's leave that. We'll make do without an optimizer. But you also need a loss function. So loss function is again the error function. So in this particular scenario, you want to use torch.nn dot cross entropy loss. So this is the loss function that you use. Again, I'm not going to details about what this is, but essentially a criterion is usually some kind of a loss function, and you can look up. There are a lot of loss functions in PyTorch, and then you can look up which is the best one for your particular setting. I think many loss functions might be covered in subsequent lectures, so you'll understand better on what kind of loss function you should choose. But right now you should just assume that this is some kind of error function where you pass in the correct tables and the output from the network, and that gives you some kind of error. Okay, and then I'll define some learning rate. So now I can start training it. For epoch in, let's say I want to run 10 epochs. So for images, labels in train loader. Yeah, sorry. So let's say you have you want to get these from the train loader. Then what you will do is you will first convert this to the correct shape. Batch size equal to images dot shape of the. So this gives you just the number of images in this batch, and then you reshape it into this size. And then you can pass it into the network to get the output. So output is equal to net images, comma, yeah, and then your loss is equal to you pass it to the loss function. Then you can do loss dot backward. So once you do loss dot, actually I forgot one thing. So before you do all of this, you actually want to zero out the gradients, because PyTorch keeps accumulating gradients unless you zero them out. So after each batch, you want to zero out the gradients, so that this accumulation, like this backward, computes the correct gradients. And then you want to update. So for param in net.parameters, so for each parameters, what you will do is param minus equals learning rate into param.grad. So I'm just doing the gradient descent step, and that should do it. Right. Maybe we can add a progress part. Just so this will just add a progress bar here. Now your neural network is essentially training. Maybe we want to print the loss, so we can add some printing here. Average loss equal to 0. Numbers. I'm just printing. I'm just trying to calculate the average loss. I think we need to use optimizer here. So optimizers, again, they just do, if you pass them, you give them the parameters, they will just do gradient descent for you. So once you backpropagate the gradients, the actual step is being done by your optimizer. It's just, again, a more convenient way of doing all of these things. So as you can see, like the loss is decreasing, which means that your error function is decreasing. So you are learning something. But let's say you want to figure out what is the accuracy. So what you will do is you will write a simple function to compute the accuracy, which will take your network and your data loader as input. So right. I'm just copying the code which computes the output. And now what you want to do is the predicted output is going to be the index of the maximum probability. Right. So I just do argmax and then add it's correct. So I add the number of correct values. Right. The correct values are when labels. When the predicted labels match the labels from the data loader, and that's the correct one. And total, I just add batch size. So the accuracy is going to be correct divided by total. So I can see what the accuracy is. Let's see. I'm not sure why it's not working. This is not working. Let me see. I mean, it often happens that like you make some sort of mistake, and then so it's not like usual programming where your mistake will show up as an error. You might make some mistake somewhere in any function, and then you have to basically look at the function and debug what went wrong. Um, Give me 1 second. Maybe I need to add. Oh, right. So the mistake is that I did not add any activation function here. Right. So this you can see that without an activation function, this network does really badly. And so this, like the accuracy is less than like even less than 1%. So I need to add. Let's see if I add a activation function after each after the first layer. Let's see if this improves. Right? Yeah. So I think there's still some mistake because the training accuracy is very low. The training accuracy should be pretty high if your network is working properly. Yeah, I'm not sure what's going wrong. Maybe if I add softmax. Yeah, I'm not sure what's going wrong here, but maybe I'll figure it out and I'll put it. Maybe there's some group or something I'll put it there.
Yeah, we can put it on a GitHub repo and on the website also.
Yeah, sure. But I hope that the broad idea is clear. The idea is that you define some loss function, define some model, and then you iterate over it in a batched fashion, and then that gives you and then you keep minimizing the loss at each step, and that will give you that will give you a function that learns how to output. Like that will give you a function that learns whatever that learns to fit the data that you want, and then you can use it to predict on things that are not in the data. And PyTorch basically gives you this autograd mechanics that you can use to compute gradients automatically, so you don't need to do all of the tedious calculations yourself. So I think that concludes the session for today. Thanks. I mean, maybe this was a bit too much material at the same time. So this is usually in the machine learning course. This would span probably 5 or 6 lectures of 1 hour each. So yeah, but I hope that you at least got something, understood some new concepts from this.
Okay, yeah. So thank you so much, Ananye, for doing this. And for everyone else, so I'm posting the link to the Google form in the chat. I've also posted it on YouTube, so you can now see the questions and answer. I think we'll give about 15 minutes, 10 to 15 minutes for you to answer. And like Ananya said, like we'll figure out the code and post it on our website and on the GitHub repo. And we'll also put it up on Discord, so you can have a look after. And I would personally definitely say to look at the talk again, go through what Ananya said in more detail. I'm going to do that myself. So yeah.
I mean, if anyone has any questions, I don't know if there's a platform to ask questions after the talk. Is there some mechanic?
We have a Discord server where we have created a channel specifically for this session.
Yeah, sure. So maybe you can add me to that, and I'll answer any questions. And
Sure.
I'll also post the code if you're there and on the GitHub.
Yeah, sure. Okay. I'll WhatsApp you the link.
Yeah. Okay.
Okay. Thank you. Thank you very much.